Example 14-7, energy calculations. For the simple harmonic oscillation of example 14-5, determine A, the total energy, B, the kinetic and potential energies as a function of time, C, the velocity when the mass is 0.05 meter from equilibrium, and D, the kinetic and the potential energies at half amplitude. X is plus minus A over 2. So in order to solve the problem, obviously we have to take a look at the example 14-5. So 14-5, we already solved that. So the first, let's just start with the definition of the energy expression out of simple harmonic oscillator of spring system. So first step is number A. We have to estimate total energy with the spring constant K 19.6 Newton per meter, and the A maximum amplitude of displacement at 0.1 meter. So as you remember, the total energy should be 1/2 spring constant K times maximum amplitude A squared. So if you plug that number, should be then the total energy is 1/2, 19.6 Newton per meter, and square the 0.1 meter. So that lead to the answer of the total energy. So that is 9.8 times 10 to 2 minus 2 joule. So that is 98 millijoule. And number B, now you know the X is minus 0.1 meter cosine 8.08 T. We already derived this formula from the 14-5 example problem. Then V is 0.808 meter per second maximum velocity times sine 8.08 T, that is velocity as a function of time. Now you plug those X and V into the potential energy and the kinetic energy as a function of time. So U potential energy is 1/2 K X squared per its definition. So that 1/2 times 19.6 Newton per meter, and X is what? 0.1 meter maximum. So that is 0.1 square. So that is, and you gotta just also square the cosine square is 8.08 T. So throw all the numbers into the formula, then the potential energy should be in this form. 9.8 times 10 to the minus 2 joule times cosine square 8.18 T. Now we need to take a look at the also the kinetic energy of the simple harmonic oscillator. So that is should be 1/2 mass V squared. So mass is 0.3 kilogram, and the velocity that is point. You have the velocity right there. We plug into this formula, then that should be 0.808 meter per second. Sine 0.848 T squared. So you fully express it and just do this mass then kinetic energy of simple harmonic oscillator should be 9.8, 98 millijoule times sine square 8.08 T. So that just to show you the two energies, potential energy and kinetic energy as a function of time based on their definition. And the number C, we have to determine the velocity when the mass is 0.05 meter from the equilibrium. So the X should be replaced with the 0.05 from maximum amplitude. So the V is the V maximum times square root of 1 minus x square or maximum amplitude square. If you plug the numbers into this formula, then point will lead to the velocity as a function of time. So the 0.808 meter per second times square root 1 minus 1 over 2 square. So speed or velocity when the mass is actually 0.05 meter away from the equilibrium is 0.7 meter per second. The D, so we have to also determine the kinetic potential energies at half amplitude. X is plus minus A over 2. So all we need to actually replace X with the A over 2, maximum amplitude over 2, then you will find out the number for the kinetic energy and potential energy. So here, when X equals A over 2, then that is same as 0.05 meter. So the potential energy U is 102 K X squared. This corresponds to the 102, 19.6 meter per second. And X is the 0.05 meter. And you got to square it. Then that is 2.5 times 10 to the minus 2 joule, which is 25 millijoule. And the kinetic energy K is total energy minus U. So all we need is actually take 25 millijoule out of the total energy, 98 millijoule. So that is 9.8 10 to the minus 2 joule minus 2.5 times 10 to the minus 2 joule. So that lead to the answer for kinetic energy, which is 7.3 times 10 to the minus 2 joule, which is 73 millijoule. For D.